Welcome to the next lecture. Today we will start digital modulation schemes. Let me first recall what we have done till now. So we had an analog signal. As an example, it can be any audio signal, or it can be any video signal, or any other signal. Okay. So what we did is we performed sampling, and we got a discrete time signal. And then we performed quantization, and we used pulse code modulation, and now we have simply binary sequence, and we used line coding, that is representing 0 by some minus level and representing 1 by some plus level, and now we have a binary sequence. Okay. Now we want to transmit this binary sequence. We want to transmit this line coded symbols. We cannot transmit them as it is over the antenna, for the reasons you definitely must be knowing. If you don't know, you have to go back to, as I told you, the basic lectures on communication systems, and you can revise the modulation. One of the reasons is antenna height, the other is multiplexing. We need to modulate them, and to modulate the signal, we need to suppose if we have a signal s of t, or let me use some other. Suppose m of t is a signal, message signal, and you want to modulate it so that it can be transmitted over antenna. So you will take a high frequency carrier signal cos omega ct. Okay. And you will for one of the techniques of amplitude modulation is you will simply do this thing, m of t cos omega ct. Now if m of t has suppose spectrum like this, then m of t cos omega ct will have spectrum as you all know. Okay, omega c minus. I warn at this point that if you still don't know this, then no one can help you at this point. Okay, this much you must have till now revise it, even if you don't know this concept. It is simple DSBSC basic AM modulation. Anyways, now we have binary 1 like this, and we have binary 0 like this. Okay, let's say it has amplitude A and this is minus A. Right, now we have to transmit it. So what we need to do is we need to multiply it with some carrier signal. Let's take a carrier signal. Suppose carrier, we take some b cos omega ct, where omega c is 2 pi fc. Fc is also called carrier signal. Okay, sorry, carrier frequency, and this fc is quite high, so fc is much high, so it can be in the range of megahertz or even gigahertz. Okay, now let's say it is b cos omega ct. For various reasons, we would like the carrier to have unit energy. Okay, there are various reasons for it. I will tell them later on, but this is the customary in digital communication. Now if you represent this carrier by c of t, suppose you want this energy of c of t to be unit energy. So how to compute the energy of this signal? So it is integral c square t dt over the time period 0 to t. Okay, let's suppose we are interested in time period tb, which is also called bit time interval. So it is a time period. Suppose this can be taken as tb. It is a time period over which we transmit one bit. Okay, so now this we want to be 1, so which means that integral b square cos square omega ct should be 1. We will use a identity that cos square theta is 1 plus cos 2 theta by 2. So then it implies b square by 2 integral 0 to tb 1 plus cos 2 omega ct dt, which is b square by 2 times tb plus b square by 2 cos 2 omega ct dt. Okay, so this part is very easy to verify that it will be equal to 0, and hence we are left with b square tb by 2. We want this to be 1, so we have to choose b to be root of 2 over tb. Okay, now hence the carrier signal can be represented as root over 2 by tb cos omega ct. Some of you might have even seen this equation before, but there might not be the reason to write the carrier in this way. So the write carrier in this way, it makes decision energy to be 1. Okay, yeah, one important fact I forgot to tell you, how this is 1. Actually fc is chosen to be some integer times over tb. Okay, so that is the reason this will be 0. Okay, otherwise it will not be 0. And this is not any bad assumption. We can always choose carrier such that it is some integer divided by the time period of this bit duration. Okay, now sorry, we represent binary 1 and 0 in this way. Okay, there is another way we can say that we say that it is root eb is this amplitude here, and minus root eb is the amplitude here. The reason of writing it root eb and minus root eb is, if you square it, right, if you square this you get eb, which is exactly the energy of this bit. Okay, when you transmit it over the tb time interval. So that is the reason for we can write it as root ep also. So it means that binary 1 is represented by root eb level of the signal, and binary 0 is represented by minus root eb level of the signal. Now to transmit you know let to transmit binary 1, so we call the signal as b of t. It is root eb, definitely for 0 less than equal to t less than equal to tb, right, for tb time interval. What we will need to do is we will write s 1 of t is equal to b of t times c of t, that is root eb times the carrier, that is under root of 2 by tb cos omega ct, definitely 0 less than equal to t less than equal to tb. So this can be transmitted over the antenna. So now if you transmit this signal over the antenna for time period tb, this will represent actually binary 1 is transmitted. Okay, so which can be written as root 2 eb divided by tb cos omega ct. So this is the representation of binary 1. And to transmit binary 0, we will write s2 of t as minus root EB, so this is one way, times under root of 2 over TB cos omega CT. Definitely again for 0 less than equal to T less than equal to TB. Okay, so this becomes minus under root of 2 EB by TB cos of omega CT. But there is one more way to represent it. I can write it as also 2 EB by TB. Cos of theta plus pi is minus cos theta, so I can write omega CT plus pi. Okay, so in other words, what we actually are doing is, to transmit binary 1, we can say, suppose we have a signal under root of 2 EB by TB cos of omega CT plus theta. Suppose this is our signal. To transmit 1, you select theta to be 0. To transmit 0, you select theta to be pi. Okay, so what you are able to do is, you are able to transmit binary 1 or binary 0 by shifting the phase, right? Shifting the phase. So this particular modulation scheme is called binary phase shift keying, BPSK. Okay, and there are two ways to represent BPSK. One is that is called baseband representation. Baseband representation means this one. You are representing B of t by root EB for binary 1 minus root EB for binary 0. So if you take this axis, you can represent it in this way, root EB and minus root EB. See, this is the simplest way to explain BPSK. Otherwise, there is a very complex explanation for this also. Maybe I will upload a separate lecture for only those who are interested in that. So this is otherwise a very simplest way to represent BPSK. Simplest explanation also. And this particular diagram where we represent the binary symbols in baseband. Baseband means without modulation. Again, in simple words, without modulation. Or in other words, baseband is also the message signal before we multiply it with cos or sine. And this diagram is called constellation diagram. Okay, so this is your BPSK signal. Now, how to generate it? How to design the modulator? It's very simple. See, what is the input? The input is, now I will write here, BPSK modulator. Okay, so I have a binary data sequence. What is the first thing I should do? I should do line coding, right? Representing 1 by some plus level, representing 0 by some minus level. So I will use something called polar non-return to 0 level encoder. It is very easy to design using op amps. What does it mean? So it means that this one. So this is your 1 level, this is 0, 1, 0. Polar means that one has polarity positive, 0 has polarity negative, and non-return to 0 means it does not return to 0, like unlike this. So this is the return to 0, 1, 0. Okay. There is another. There are a lot of types. Bipolar, no return to 0. Then there is a Manchester signal. So line coding is a separate topic, but this is the simplest way. We are using this line coding. Okay. Then what we should do? We should use product modulator. Product modulator will simply multiply the carrier signal. I represent the carrier here now with 5 symbol. Okay. This phi 1 of t is the carrier, just to be compatible with Simon-Huygens notation. So it is unit energy signal, and I will get the output BPSK binary phase shift keying signal, which is represented by S of t. Okay, very simple modulator. So here in product modulator, you can use any product modulator you might have studied. Okay, any DSBSC modulator or any product modulator you can use. Now modulation is pretty much simple. Now I need to demodulate it. So BPSK demodulate. So let me first discuss BPSK demodulator, and we will basically, let's say that there is no noise. Now let's see this. So you have S of t as it can be anything plus minus root of 2 EB by t, depending upon whether it is 0 or 1, cos 2 pi FCT, right? This is the BPSK signal. Now how to get back the original? See, what is your message? Your message is either root EB or minus root EB. Okay, this is your message. Now let me represent it by B of t, so that we don't have to write the symbol FC. Okay. Now the first thing we do, even in your usual AM demodulators or any other demodulator, you multiply back this carrier S of t phi 1 of t, which is S of t under root of 2 by TB cos 2 pi FCT, right, which is B of t under root of 2 by TB cos 2 pi FCT square. So it becomes 2B of t by TB cos square 2 pi FCT okay, and this becomes, using the identity of cos, 1 plus cos 4 pi FCT. Okay, so which becomes B of t over TB 1 plus cos 4 pi FCT. Now this will not help. There is this 4 pi cos FCT. Okay, so one of the simplest explanation which I can give you here is, see, if you look at it closely, there are two terms, B of t over TB plus B of t cos 4 pi FCT over TB, right? So this is the baseband term. It is of low frequency, and here cos is multiplied with it. FC is a high frequency, so this is the high frequency term, right? So the simplest solution is to use low pass filter. When you use low pass filter, the output will be B of t over TB. Now From this you can easily identify whether 0 was transmitted or 1 was transmitted. How? So if B of t is root EB, right, then B of t will be greater than 0, which implies 1 was transmitted. Okay. Sorry. Else, if B of t is minus root EB, that is, it will be less than 0. We just have to check the sign. Amplitude does not matter. This is the power of digital communication. So it means that even if noise will deteriorate the amplitude, we will not lose the information easily. So it means 0 was transmitted. Okay. Now you see, those of you who have done the basic electronics course, low pass filter is realized by a circuit called integrator. Okay, something like this. You might have seen the op amp, and there is a capacitor here. Right. So if you give any signal here, okay, so this I think the capacitor is in shunt. Yeah, this is in shunt. This is the integrator. So this sorry, this circuit will allow only high frequency signals, but will not, sorry, will allow only low frequency signals but not high frequency signals. But let me tell this operation in a different way. I can, for those who don't understand it. See, before the low pass filter, what was the output? It was B of t over TB plus B of t over TB cos 4 pi FCT. If you integrate this from 0 to TB, okay, dt, right? So this will be integral 0 to TB B of t dt plus integral 0 to TB B of t cos 4 pi FCT dt. See, B of t is either plus minus root EB, right? So that's constant. So there will be TB only here. Plus similarly here, this plus minus root EB will come out. Now since FC is chosen as integer times divided by TB, so this integral is simply 0. And TB gets cancelled out, so you have here just plus minus root EB. Now if it is plus root EB, then you know 1 was transmitted. If it is minus root EB, then you know 0 was transmitted. Okay, so now we can realize the demodulator like this. So let's denote by x of t the received signal. So here I am taking a noiseless case. So x of t is itself this s of t, okay, which is anything under root of 2 EB by TB cos of omega ct. You can also represent it by B of t under root of t to 2 by TB cos omega ct. Okay, so what you first do is you take this x of t, you multiply it with the carrier, that is phi 1 of t. That is what we did in the modulation first. Then you can use here low pass filter also. That is equivalent to saying we will use integrator, which will integrate this. Then the output of integral, I will represent that by here x1. What is this x1? After integrating, this is your x1. So x1 is either plus root EB or minus root EB. Then you have to check the sign of x1. So to check the sign, we have a device called decision device. Those of you who have done basic electronics course, we have a circuit called comparator. basic electronics course in NIT Srinagar, in uh, other universities I know, in IUST also. It is taught computer science people also, electrical people also. So no excuse for that. That I am from computer science background, electrical background, I don't know. This is a basic subject. Okay. Decision device can be realized using comparator. If you don't know comparator, kindly go search and see some book. A very basic op-amp based device which will take any input and the output will tell us a sign whether it is plus or minus. That is decision device. So decision device has to make decision with respect to some threshold. Here the threshold is 0, that is it has to compare with 0 whether the input signal is greater than 0 or less than 0, and it will give a decision that choose binary 1 was transmitted if this x1 is greater than 0, choose 0 was transmitted if x1 is than 0. Okay. Sorry. And this operation, the operation of multiplying and integrating, is also called correlation operation. This is called correlator. And since we are generating carrier here at the receiver, this is the demodulator receiver. So see, this is BPSK demodulator. Since we are generating this BPSK signal here, it is also called coherent detection or demodulation. Okay. Now at this point you may say that, okay, go back to the BPSK signal, basic signal. So that was root 2e by t cos of 2 pi fct plus theta. This was one form of writing it where we said that we put theta equal to 0 for binary 1, we put theta equal to pi for binary 0, right? Some of you may easily say that, what if we take more phases on instead of only 2 phases? Okay, suppose I now represent a signal. I will write Si of t as under root of 2e over t cos of 2 pi fct plus some theta. Okay, definitely for 0 less than equal to t less than equal to some capital T. Now what I will say is, let me write here theta I. Okay, so I may choose, suppose theta I to be some particular phase. Let me say any phase. So we will choose theta 1, theta 2, theta 3, theta 4. Let's say only 4 phases I choose. So if I take theta 1, I will get 1 signal. If I take theta 2, I will get 2 signals. If I take theta 3, I will get third signal. Similarly 4 signal. See, mind it, remember, for BPSK we had chosen 2 phases, so we just got two signals, and hence we were able to represent either binary 0 or binary 1. So BPSK at a time would transmit 1 bit, right? Now here we have 4 phases. I can now represent 2 bits at a time. I can say that if I choose phase theta 1, I will call that will denote if 0 0 was transmitted. Otherwise theta 2 means 0 1, theta 3 means 1 0, theta 4 means 1 1. Okay, to put it more formally, let me suppose I choose Si of t as under root of 2e by t. See, mind, I'm not now using EB or TB. That was for bit energy and bit time interval. Now I have 2 bits I'm representing. So I'll write E and T. Okay, cos of 2 pi fct plus, I will write here 2i minus 1 pi by 4. Just look at it. And here I write 0 less than equal to t less than equal to t, capital T, and I is equal to 1 2 3 4 and 0 elsewhere. Okay, Now what does it mean? Suppose if I put I equal to 1, okay, then what is this phase term? It is pi by 4. So you get Si of t is equal to under root of 2e by t cos 2 pi fct plus pi by 4. If I choose I is equal to 2, I will get 3 pi by 4. So sorry, is S1. S2 of t is equal to root over 2e by t cos of 2 pi fct plus 3 pi by 4. If I choose I is equal to 3, okay, so I will get 5 pi by 4. So S3 of t is under root of 2e by t cos of 2 pi fct plus 5 pi by 4. And if I choose I is equal to 4, I will get 7 pi by 4. S4 of t is under root of 2e by t cos of 2 pi fct plus 7 pi by 4. Now what does it mean? It means that out of your sampling and quantization and pulse code modulation, you are getting a sequence of zeros and ones. Now if you get consecutively 2 zeros, then you will transmit this signal to represent 2 zeros. If you get consecutively, suppose here 0 1, then you will transmit this signal with this phase for 0 1. If you get consecutively, suppose 1 0, then you will transmit this signal for that. If you get consecutively, suppose 1 1, you will transmit this signal for that. So you are able to transmit now a signal which represents 2 bits at a time, right? Sorry. So definitely you get double data rate than the BPSK. There are actually two ways to look at it. Either you choose t as same as tb, then you get double data rate, or if you choose 2 is equal to 2 tb, then what you are choosing a longer time interval, hence you save the bandwidth. Okay, so this concept we will discuss later on. So I think this much is clear. Now this type of modulation where we are able to represent we have 4 signals which represent 2 bits, any of the combinations, it's called quadrature. Quadrature refers to 4 phase shift keying. QPSK. Okay, now to get a more clear picture of QPSK, we will represent it in little bit in a different way. Okay, let me rewrite this equation. Si of t is under root of 2e by t cos of 2 pi fct plus 2i minus 1 pi by 4 for I is equal to 1 2 3 4, and this t is between 0 to capital T. Before I move forward, okay, let me make a pause here. BPSK, the high frequency signal is suppose this, right? Then if you have suppose 1 0 1 1, how it will be represented waveform? So this is the time interval TB. So 1 means for this time interval you have a signal with 0 phase like this. Then you have a 0. Okay, so its phase will be something like this then. Okay, then you have a 1, so it means it will start from this. Then you have a 1. Okay, so what you will do is after every TB time interval you will check the phase actually that represents whether it is 1 or 0. Okay, so this will be visualization of BPSK. Now coming back to this, I will use cos of a plus b. Sorry. Cos of a plus b is cos a cos b minus sin a sin b. So cos of 2 pi fct cos of 2i minus 1 pi by 4 minus cos of 2 pi fct cos of 2i minus 1 pi by 4. Sorry, it is sine now. Okay, sine of 2 pi fct sine of 2i minus 1 pi by 4. Okay, you can look at this in a different way. You can think of, see, this is the carrier part, right? Including, so this is the carrier part. Let me write it in again. So I can write under root of e times cos of 2i minus 1 pi by 4 root 2 over t cos of 2 pi fct minus under root e sine of 2i minus 1 pi by 4 root 2 over t sine of 2 pi fct. Okay. So if you look, this is the carrier part, and here it is a sine, which is the carrier part. So it is as if there are two carriers. So I represent this by phi 1 of t and this by phi 2 of t. Okay, so we can write it as root of e cos 2i minus 1 pi by 4 phi 1 of t minus root e sine 2i minus 1 pi by 4 phi 2 of t. Okay, so these are the carriers. They are also called quadrature carriers because they have pi by 2 phase difference. Now, what is their baseband part? See, cos and sine are having pi by 2 phase difference between them. Okay, in fact, we note here very important thing. Suppose if you take this phi 1 and phi 2, phi 1 is under root of 2 over t cos of 2 pi fct, phi 2 is under over root of 2 by t sine of 2 pi fct. If you look at phi 1 of t times phi 2 of t and integrate it over the interval 0 to t, just verify it at your places. You will get t square, then this is cos of omega ct sine of omega ct, and it will come out to be 0. Just look at it. And we also know that phi 1 square dt, this is 1, phi 2 square t dt, this is also 1, because we have chosen carriers to be of unit energy. Now if you compare it with, if you think of this like this, you have two vectors a and b, and this is their dot product, a dot b is equal to 0. Suppose I, j, k, these are the three unit vectors. What are their properties? I dot j is 0, right? J dot k is 0, so on and so forth. Similarly, I dot I is 1, j dot j is 1. They are the unit vectors and you can represent any other vector in terms of unit vector. If you define dot product of functions as integral, suppose you have two functions f of t and g of t. If it is defined integral of f of t g of t dt as a dot product over some time interval and represented by f of t g of t, this is called a dot product or inner product. This is analogous operation to the dot product in vectors. Then you can say that functions f and g are orthogonal if the dot product is 0. That is if the integral f of t g of t dt is 0. And sorry, and they are in particular orthonormal, that is they are normalized if the dot product of f with itself is 1, that is integral f square t dt is 1. In this sense, if you look at phi 1 of t and phi 2 of t as defined above, they form the orthonormal pair of functions. Okay. So like ijk is used to represent, suppose you have 3I plus 4j. What is this? It is a point in this plane, so you represent along the x-axis the I vector, along the y-axis j vector, and you move 3 points here, 4 points here. So you say that this point 3, 4 represents this vector. Now you come back to this point. See, this is your sorry, Si of t. Okay. Now if you look at, we think of phi 1 of t as a unit vector, phi 2 of t as a unit vector. Okay, so you can think of them as two axes, and then root e cos 2i minus 1 pi by 4, root e sin 2i minus pi by 4, they are the points. It will become very clear what I am saying. Suppose you take this binary sequence, suppose you take 1 1, okay, 0 1, 0 0 1 0. By the way, this way when I write the sequence, it is called gray coding. Gray coding means when I move from 1 1 to 0 1, only one bit changes. When I move from 0 1 to 0 0, only one bit changes. When I move from 0 0 to 1 0, only one bit changes. So this is the gray coding. Okay, gray coded bits, input bits. And let me write here I and here phase. When I is 1, what is the phase? 2i minus 1 pi by 4, right? So this is pi by 4. When I is 2, it is 3 pi by 4. When I is 3, it is 5 pi by 4. When I is 4, it is 7 pi by 4. It is up to you. You want to map 1 1 to any other phase? Do it. But once you do it, you have to fix it. You can't change it. I mean, transmitter receiver should know it. Okay. Now after choosing it, what is the value of this term? So let me write here. The first term is root e cos of 2i minus 1 pi by 4. This is root e including this sign, root e sine of 2i minus 1 pi by 4. Okay, so you just compute it. Cos of pi by 4 is 1 over root 2, so it will be plus root e by 2. Similarly, sine of, okay, it's here, sine of this pi by 4, that is also 1 over root 2, so it will be plus root e by 2. 3 pi by 4 you compute cos, it will be minus root e by 2. It will be plus root e by 2. 5 pi by 4, it will be minus root e by 2. It will be minus root e by 2. Similarly, it will be plus root e by 2 minus root e by 2. Now what I want to say is, if you now represent here this axis as phi 1 axis, that is it, this axis is along this cos function, okay, and this axis as phi 2 axis. Then these 4 points, suppose 1 1 is plus root e by 2 plus root e by 2, So this is the 0.11. Okay. Similarly, this point is minus root e by 2 and root e by 2. So this is 0, 1. Similarly, this point, which is at the phase of 5 pi by 4, this is minus root e by 2 minus root e by 2. This is 0, 0. Similarly, this is root e by 2 minus root e by 2. This is 1, 0. And if you look at it carefully, sorry, this phase is pi by 4. This is 3 pi by 4. And then this much phase from this x-axis, it is 5 pi by 4, and this phase is 7 pi by 4. Okay, so this is the baseband representation of QPSK. Okay, and it's also called constellation diagram. And now how to modulate and demodulate, I will show that in next class, but let me just show here. For modulation demodulation, look at this equation. See, if you understand BPSK, all other modulation schemes will become easy to understand, because if you look at QPSK signal here, you can think of this as there are two BPSKs. One BPSK term is here, the other BPSK term is here. So you basically have to, in some sense, perform twice BPSK modulation, one with cos, one with sine. Same is at the receiver part. So that part we will see tomorrow. So these are two famous modulation techniques. There are other modulation techniques also. Now, instead of just choosing 4 phases, you can choose m number of phases. We call that m phase shift keying, MPSK, out of which 8 PSK is the famous one and is the only one which is used. Okay, and then there is a famous modulation technique called m-QAM. This also we'll do in next lecture. We will do the modulation and demodulation. Now, we are right now doing everything without error. After this, we will do the analysis of error. Sorry, we are doing everything without noise. After this, we will see the performance of these modulation techniques in presence of noise. This lecture was a little bit lengthy, but was necessary. So now, understand it properly. Then we will take up other modulation techniques. Thank you.